Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is Muhammad Alif bin Muhammad Noor. So first of all, I will start with the introduction of our project. Okay, our task is to create a trajectory that will allow the X-arm robot to draw the first letter of each team member name. So since our name is Hairul, Siti, Alif, Zulkarnain and Daniel, so we decide the X-arm robot to draw letter H, S, A, Z and D. Next, for the robot model, we design the 6 degree of freedom robot by using SolidWorks. 6 degree of freedom means that the robot will have 6 joints, which are the base rotation, the linear transitional, the shoulder rotation motion 1, the elbow rotation motion 1, the elbow rotation motion 2, and last but not least, the end effector. The picture shows the assembly of the robot.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Zulkarnain bin Zakaria, ID FB17037. Today, I would like to present about the DH algorithm and then the forward kinematics equation. Okay, first, derivative Hartoven parameter, which is there are several steps. Step 1 is establish the base coordinate system. Step 2, align Z I axis with the axis of the motion or of joint I plus 1. Step 3 is establish the origin of the I coordinate system at the intersection of Zi and Zi minus 1, or the intersection of the common normal between Zi and Zi plus 1 minus 1 axis and Zi axis. Step 4 is establish the Zx xi axis using the formula. And then step 5, establish the yi axis using the formula stated. Next, the diagram show that the x and x, y and z axis of the robot coordinate system. And then the step 6 is to establish the hand coordinate system, which is the end of the effector. Step 7 is join the link of parameter, which is di. For this case, there are two di, which is d1 and d4. For the join and link, then step 8 is join and link parameter for ai there. And then step 9 is join and link parameter for theta and alpha. Next last step for the DH in this case. So step 10 is establish the DH parameter table, which is there are 6 joints, and there the I, AI, alpha I, and theta I for the robotic system. Next, for the forward kinematic equation, is a continuous of the DH parameter. Then for the step 11, we calculate the DH transformation matrix, which is we insert the value of the joints at this and we get from 0a1 until 5a6. And then step 12 is kinematic equation of manipulator. So we want to get the transpose of 0 until 6. We need to matrices all the of 0a1 until 5a6. And then this is the last answer of forward kinematic equations.
Assalamualaikum and hi, my name is Siti Zahra Bididin. So I'm going to proceed with the inverse kinematic. Finding the joint angle of a robot manipulator using the location and orientation of the robot's end effector is an inverse kinematic issue. The final forward kinematic equation is employed here to calculate the joint and link parameters. So by multiplying the inverse of the A1 matrix with the whole transformation matrix, the following joint angle values 1 and 3 are derived from equation in forward kinematic. So by solving the above equation, angle 1 and 3 are obtained. The following joint angle theta 2, theta 4, theta 5, theta 6 are obtained by multiplying the inverse of negative A1, A2, A3 and A4 with the whole transformation matrix. And last but not least, by solving the above equation, angle 2, 4, 5, 6 are obtained. That's all from me. Thank you.
Assalamualaikum. My name is Muhammad Dinina Ibn Zulkifli. Okay, so I will present to you about the simulation. First is the trajectory plotting. So first we must decide the letters first. For our group, we choose the letter which are H, S, A, Z and D. And then for each of the letter, we define how many strokes you have to produce the letter. So below is the visualization of each of the letter shape. So this is the number of strokes for each of the letter. Okay, next is the Simulink and SimScape multibody. The Simulink is a dynamic and software MATLAB integrated simulation and model design system. It can be used to design, simulate, and verify every aspect of the autonomous system. It provides a multibody simulation environment for 3D mechanical systems such as robots. The multibody also formulates and solves the equation of motion for the complete mechanical system. By using the multibody, we can import the existing complete CAD assemblies, including all the meshes, initials, joints, constraints, and 3D geometry into the MATLAB. Okay, so next is the Simulink block diagram. So, as we can see above, a block diagram consists of blocks that represent different parts of a system and signal lines that define the relationship between the blocks. So, in this project, by using our robot design as above, we can visualize the relationship between the joints of the robot. So in this diagram, we can see that because the robot has 6 degrees of freedom, the block diagram shows that the 6 joint is dependent on each other. Okay, so next in this project, we use the Peter Cock robotic toolbox. So we use guide to book the GUI. It features the edit box and the buttons. So in this GUI, the user can input the theta value and click forward to enable the forward kinematic operation. The user also can input the effector coordinates of x, y, z and click the inverse to allow the operation of inverse kinematics. So for example, for the forward kinematic, we fill all the theta and then the robot will visualize in the figure, and then the coordinates of the effector will be automatically calculated and shown in the edit box. Same also for the inverse kinematic. When we input the coordinate of the effector x, y, z, we will automatically calculate the angle of the theta.
For conclusion, in summary, we successfully integrated required kinematics up to MATLAB environment. The X-arm robot seamlessly designed on SolidWorks environment with details up to mark. Then this design be transferred to Simulink environment for greater immersive simulation. For kinematics and inverse kinematics carefully derived for much better arm movement and error-free. For me, these two kinematics is very important for this project where the algorithm is heavily used to determine the movement of this X-arm. Theoretically, when every coordinate is being keyed based on XY plane for every word, the algorithm will figure out on what joint to be rotated at a certain degree. All this thanks to both forward and inverse kinematics derived earlier. So, the arm will be moved accordingly on the workspace that derived on this MATLAB and following the path that been left by our initial name, as previously mentioned. However, this project meets their block versions where the simulation cannot be done automatically and need to be done manually, as we can see on the result. This is because of the novelty of this revised project and very tight time constraint given where revised version is completely intangible from original ones. Is changed on week 10. In future, with better time flexibility and strict ahead planning, this project may be great where real robotic arms will be heavily used and interact with for more and better understanding for us. Simulation uses may be useful, but it needs more supplemental cadence and time as discussed previously, where another novel topic needs to discover. Thank you.